Hello everyone and welcome to Soil Moisture 201. Today's presentation will be 20 minutes followed by 10 minutes of Q&A with our presenter Leo Rivera, whom I'll introduce in just a moment. But before we start, a couple of housekeeping items. First, we want this to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll keep track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, no problem. We're recording the webinar and we'll send around the recording via email within the next 3 to 5 business days. All right, let's get started. Today we'll hear from Leo Rivera, who will introduce moisture release curves and how they can be used to understand your soil at a deeper level. Leo Rivera operates as a research scientist and hydrology product manager here at Meter. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in Meter's hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. So without further ado, I'll hand it over to Leo to get us started.
Thanks, Brad, and thanks everybody for attending today's virtual seminar. So this is meant to be a follow-up to Soil Moisture 101, which was aired a couple months back. And we're going to focus on similar topics. You learned about water content and water potential in 101, but in 201, we're going to take a deeper look at water potential and then a deeper look at soil moisture release curves and what they can tell us. So first, I'd like to start with a brief introduction about myself. My background is in soil physics and pedology, and a lot of that work that I did with the NRCS when my project was looking at the effects of landscape position and land use on soil hydraulic properties. And beyond that, I've had 12 years of experience measuring and interpreting soil hydraulic properties and soil moisture release curves. I've had many conversations with several researchers looking at different moisture release curves and looking at their different soils and trying to understand what's going on, what the soil moisture release curve is telling us, and how we can use that information to help us make better decisions. And a lot of that's going to come out in today's virtual seminar. So I think first I'd like to start off with this question. This was the same question that was brought up in Soil Moisture 101. What does soil moisture even mean? Well, it really depends on what your research goals are and what you're ultimately trying to understand. So are you interested in just water stored in soil? Is that your main goal? Do you care more about water available for primary productivity within the ecosystem? Are you studying water and solute movement in soils? Or is your goal to optimize water use of crops? Or one of my favorite topics, are you modeling soil hydrology? Depending on which of these categories you fit into, there are different aspects of soil moisture you need to understand. For some categories, for example, if you're just interested in water stored in soil, you really just need to understand volumetric water content. But if ultimately your goal is to understand how plants and other creatures are going to interact with the water within the system, you really need to understand both water content and water potential. So at the end of this virtual seminar, here are my goals for you to take away from this virtual seminar. One is that I hope you have a better understanding of the importance of water potential, because to me, it's a really important factor, and for many researchers it is. Two, how can you utilize the soil moisture release curve just for basic irrigation planning? And then we're going to dive deeper and figure out what additional information lives within the soil moisture release curve and how can you use that to help push your research or your practice to ultimately help you achieve your goals. And the last one is we'll kind of take a little bit deeper look at what factors actually affect field capacity. So before we dive deep into the content and into water potential in the soil moisture release curves, I think it's really important to understand this concept of extensive versus intensive properties. So there are two variables that are necessary to describe the state of matter or energy in the environment. You have the extensive variable, which describes the extent or amount of energy or the amount of matter or energy. And then you have the intensive variable, which describes the intensity or the quality of matter or energy. So here, let's look at some examples of extensive and intensive variables. So you have a very basic concept of volume, that's your extensive variable. And then density, which is your intensive variable. Okay, and now we're going to jump into what we've been discussing, water content. Water content is our extensive variable. It describes how much water is there within the environment. Water potential is that intensive variable, which describes the intensity or the quality, or in most cases, the availability of water in the environment. And I like these last two examples because I think they really help bring home this concept of heat content, which describes how much heat is stored within the environment, and temperature, which describes the quality, or it really describes how your body perceives hot or cold. So to take a deeper look at this, I have these two examples here. We have this large ship that's in the Arctic, and we have this hot rod that's just been heated in a fire. Okay, which of these two items has a higher heat content? The ship in the Arctic actually has a higher heat content than this hot rod here. But out of these two, which actually has the higher temperature? Obviously, the rod that's just been taken out of the fire has the higher temperature. So of these two variables, which is going to tell us, if we were to put this hot rod in contact with the ship, how is the energy going to flow? Well, it's temperature. Temperature is our intensive variable. This is going to tell us how energy is going to move. Okay, so it's going to move from high temperature to low temperature. It's a very similar concept to water content versus water potential. Water content is not going to tell us much about how water is going to move. Water potential is that main governing factor. So what is water potential? You've already discussed this a little bit, but let's take a deeper look. Here's the basic definition of water potential. Water potential is the energy required per quantity of water to transport an infinitesimal quantity of water from the sample to a reference pool of pure free water. Okay, what does that all mean? Simply, it tells us in the soil or in a pore structure how available that water is, or how much energy it would take to pull that water out. This obviously affects plants or how water is going to move. This is the governing factor. Well, what makes up water potential? There are four main components that make up total water potential. We have matrix potential, which describes the absorption of water to surfaces or within pores of soil. We have the gravitational potential, which is primarily related to its position within a gravitational field. We have the osmotic potential, which is governed by the amount of solutes in the water. So the higher the solutes, the higher the osmotic potential. And the pressure potential, which is a measure of the hydrostatic or pneumatic pressure. This is more so comes in play when we're looking at saturated conditions. But what factors are of most importance in unsaturated conditions? Well, primarily matrix potential and osmotic potential. In many cases, osmotic potential is pretty small, so it doesn't play much of a role. And gravitational potential is typically quite small, so it also does not play much of a role in terms of plant water availability. Now, there are cases where it does play a bigger role, especially if you're trying to describe water movement within the soil. So it is important that you understand that, but we're not going to take a very deep look at gravitational potential today. So here we have a picture of a soil moisture release curve, and we often refer to a soil moisture release curve being like a fingerprint for soil. And that's because soil moisture release curves are very unique to the soil. It's not just the soil texture that affects the soil moisture release curve. It's the bulk density, it's the amount of organic matter, it's the actual makeup of the pore structure. There are a lot of things that affect the soil moisture release curve. And so it's really important to measure that and understand how it's going to differ from site to site and soil to soil. And the beautiful thing about the soil moisture release curve is this is what ties together that extensive variable of volumetric water content with that intensive variable of water potential. So how can we start utilizing soil moisture release curve? Well, let's focus on a very basic concept. How can we utilize a moisture release curve to make irrigation decisions? Well, to really make good irrigation decisions, we need to understand, one, volumetric water content, because this is going to tell us how much irrigation we need to apply. We need to understand water potential because it's going to tell us how available that water is to crops or plants within the ecosystem. And it's also going to tell us where to stop so we don't over irrigate and wind up losing water and wasting water. So let's go back to the same set of soil moisture release curves that I just showed you, and let's take this silt loam as our example. So let's say our current field conditions are minus 100 kilopascals, all right? And in this silt loam, that correlates with a water content of 0.24 meters cubed per meters cubed. And let's say our full point that we're trying to irrigate to is minus 33 kilopascals. And in this silt loam, that correlates with a water content of 0.32 meters cubed per meters cubed. All right. So now we know what our set point is and our current point. And our irrigation zone, let's just take this an example of a 15 centimeter deep root zone that we're trying to irrigate to, or 5.9 inches. And what we can do to calculate our irrigation requirements is we're going to take the difference of our set point minus our current point and multiply that by the rooting zone depth. And that means we're going to have an irrigation requirement for this silt loam soil of 1.2 centimeters or 0.47 inches. Now let's jump over to the fine sandy loam curve on this graph. All right, let's say we have the exact same field conditions. Our current set point is measured point is minus 100 kilopascals. And in this fine sandy loam, that correlates with a water content of 0.1 meters cubed per meters cubed. And again, we have the same full point of minus 33 kilopascals, which in this fine sandy loam correlates with a water content of 0.16 meters cubed per meters cubed. And given the same rooting depth or irrigation zone depth, and using the same calculations we used earlier, we see that for this fine sandy loam, we actually have an irrigation requirement of 0.9 centimeters or 0.35 inches. So a little bit less than what was required. That's because if we were to try to irrigate more than that, we would potentially lose water due to free drainage. So we have to understand that. And the main takeaway point here is that all of these different soil types are going to have different set points, and it's helpful to understand this relationship of water content and water potential to help us make better decisions about irrigation and to more wisely use the water, and also to help make sure we're providing enough water to the plants for productive growth. Okay, well, let's go a little bit beyond that. What factors limit plant water availability? What other factors can limit plant water availability? Traditionally, when we think of the plant available water, we're primarily looking at field capacity and permanent wilting point. Okay, those are the typical factors that we're going to look at. But what other information is in the soil moisture release curve that can help us understand how our plants are going to behave and what might actually limit our plant available water? Okay, well, I'm going to bring to light an example of a topic I was working on with a researcher a few years back. I was working with a researcher who had a soilless media, and they were beginning to see plant stress at minus 10 kilopascals, which is significantly wetter, or so a much higher water potential than we would expect to see plants stressing at. So what's going on there? Why were these plants beginning to stress at such a high water potential? Well, we decided to dig a little bit deeper and go ahead and actually measure the soil moisture release curve of this material and try and see if there's any information in there that can help us understand why the plants were beginning to stress. And once we actually took this measurement, there was one thing that really popped out to us was, well, this soil moisture release curve showed a bimodal relationship, and that's where you see these two humps in the curve, that bimodal distribution, or that bimodal characteristic of the curve, and that second hump correlated perfectly with that minus 10 kPa point where plants were beginning to stress. So what's going on there? Why are the plants beginning to stress? Well, one of the things that a soil moisture release curve can tell us is the pore size distribution of soil. So if we were to look at a curve, for example, that silt loam curve that we looked at earlier, where you see a very smooth, gradual drop off in the soil moisture release curve, that tells us that the pore size distribution of that soil is actually well graded. Okay. Then we take for light that fine sand example, where you see a very steep drop off in the soil moisture release curve, and then a plateau at the end. Well, that tells us that this soil is fairly uniformly graded and it has an even pore size distribution. So what does a bimodal curve tell us? Well, a bimodal curve like this tells us that the soil is actually gap graded. So for example, here we actually have this soilless media that's made up of a bark material and then fines around that. Within the bark itself, we have lots of small pores. And then around it, with the fine materials that make up the actual structure around the bark, we have large pores, but we're actually lacking those intermediate pores. And so that is starting to help paint a picture of why these plants were beginning to stress. And now we're starting to understand, okay, this is why we're starting to see it at minus 10 kPa. But what are the physics that's going on there, and why are we actually seeing plants begin to stress at this point? And we'll dig a little bit deeper into that here in just a moment. I'm going to change gears here just a little bit and actually now start talking about field capacity. And here we have a basic definition of field capacity, which is the content of water on a mass or volume basis remaining in a soil 2 or 3 days after having been wetted with water and after free drainage is negligible. So in literature, we typically refer to that as minus 33 kilopascals, and that's been the rule of thumb for many years, many decades. But is that really what we see in the field? So here we have some actual field measurements of water potential. So these are field measurements from a site here in Pullman, where we're measuring with tensiometers in a silt loam soil. And what we're seeing is after a significant wetting and a time of a long period of stabilization, the tensiometers are stabilizing at much higher water potentials than minus 33 kilopascals. We're seeing them stabilize at minus 5 kilopascals and even minus 2 kilopascals. So what's going on? Why are these stabilizing at a much higher water potential than what we would expect to see based on traditional field capacity? And does this represent what I'm going to see in my soil? Well, it really depends on a lot of factors. And I think what I'm trying to say here is that it's really important to understand your site and the properties of your site to really understand what true field capacity is going to be. So one of the main things that can govern field capacity is water table height. So here we have an example of a silt loam soil and the water table position. Right at the interface of the water table, the water potential is going to be 0 kilopascals. And as you go further up in the profile and move away from the water table, you're going to see a decrease in the water potential. It's going to get drier. And depending on where you're measuring within the soil, your field capacity is going to be different because the water table is actually governing what that field capacity is. And so there are several factors there: your height, your actual measurement position, and the height of the water table that's going to govern field capacity. Now let's take this other example where we have a fine textured soil sitting over a coarse textured soil. So say we have a lithologic discontinuity, or something's happened here where we have this coarser textured soil as a sublayer. And what's going to happen when we wet that fine textured soil up and allow it to drain, as it drains at its interface with the coarser textured soil, we have a capillary barrier. And because of that capillary barrier, that interface, the water potential is going to be around 0 kilopascals. And it's going to behave very similar to like our water table example, where from there, as you move up, our water potential will begin to increase or decrease. So essentially what this capillary barrier is doing is increasing the water holding capacity of the soil and shifting what that actual field capacity is. And so the main takeaway here is that really, in order to truly understand field capacity, you need to understand more about your site. You can't just look at the soil and say, okay, this is going to always be at minus 33 kilopascals, because that's not the case. There are a lot of factors that can affect that. And now we're going to change over to actually talking about tools for measuring water potential. So one of the issues that still exist with water potential and its measurements is there's really not a good tool to measure the full range of water potential. So in order to properly select an instrument or a sensor for measuring water potential, you need to understand what your goals are and what ranges of water potential you want to measure. This is one of the reasons a lot of people opt for measuring water content over water potential, because it's just an easier measurement to make. But water potential obviously plays a much larger role in how the water can be used and how it's going to move. So we have lab instruments that are well suited for the wet end, like pressure plates or the high prop. And we have lab instruments that are suited for the dry end, things like a VSA or a dew point instrument like the WP4C. And then we have our field sensors. So we have things like granular matrix sensors, heat dissipation sensors, and things like the Terrace 21 or MPS6 sensors that give us a much broader range, measuring range in terms of water potential, but they sacrifice accuracy. And then we have a tool like a tensiometer, which gives us a much higher accuracy, higher quality measurement of water potential, but it's limited to the wet range. So as you're thinking about these tools and which one to pick, you have to think about what your overall goals are. If you're interested in plant available water and getting a larger range, then something like heat dissipation or a Terrace 21 is going to be the way to go. If you're interested in water movement, then a tensiometer is probably going to be better suited for you because you're going to be more interested in the wet end of water potential. And I would like to think back to where we were 15, 20 years ago. It used to take 3 to 6 months to get a full high detailed soil moisture release curve. And we've come a long way now. We still have a long ways to go, but we've come a long way in terms of being able to measure the soil moisture release curve. We now have tools that can give us high detail soil moisture release curves in a matter of 2 weeks. And there's so much more information now that we can gather out of those soil moisture release curves because of the improvement in the detail and obviously the improvement in the speed that it takes to get these soil moisture release curves. You have tools like the HyProp that can give us the wet end of the soil moisture release curve, and tools like a WP4C that can give us the dry end of the soil moisture release curve. What else can a soil moisture release curve tell us? I'm not going to talk in depth about these topics, but I'm going to throw them out there as things that are being done and things that are that other information that lives within the soil moisture release curve. One application is we can use the soil moisture release curve to actually predict the shrink swell capacity of soil. So we can look at the slope of the dry end of the soil moisture release curve and see that a soil with a steeper slope on the dry end of the soil moisture release curve has a much lower shrink swell capacity than, say, a soil on the very right here that has a more gradual slope in the soil moisture release curve and has a much higher shrink swell capacity. There are tools available to take these slopes and actually categorize the shrink swell capacity of these soils. So there's work that's been done on that for a long time and continuing work that's going into that. We can also use tools for measuring soil moisture release curves to help us predict cation exchange capacity and soil specific surface area. And there's a lot of work that's going on in this area to actually help better understand what this information is telling us and how we can better use these soil moisture release curves to gather this information out of the soil. So there's a lot of information that still needs to be unlocked and better understood about the soil moisture release curve. And now I'm going to actually jump back into that example of that soilless substrate that we were talking about earlier. So that soilless substrate on here is the McCorkle sample. And we were trying to understand, okay, what's actually limiting the water movement or what's actually causing this stress? And one of the things that we found, so the awesome thing about using the HyProp is not only did we get the soil moisture release curve, but we're also able to measure unsaturated hydraulic conductivity. And what we found is this McCorkle sample had a much lower unsaturated hydraulic conductivity at a much higher water potential than we would typically expect to see in soils. Even at -8 kilopascals, we were starting to measure very low unsaturated hydraulic conductivities. So what's going on? Well, what's actually happening is as the plant roots are using up the water, typically you would get a redistribution of the water towards the roots as they're pulling that water out. But as the hydraulic conductivity drops, it begins to limit that movement. And so the interface around the roots, the soil and root interface, is experiencing much lower water potentials than what we're actually measuring because of that limited movement of water. And so what we were starting to understand is, okay, it's not just water potential or the soil moisture release curve, but also unsaturated hydraulic conductivity was becoming a limiting factor for the availability of water to plants. And this can be used to help us make better decisions about designing substrates and to help us better understand how plants are going to behave in different materials and even soils, because we see this in some natural soils as well. So that was a really cool piece that we were able to see. And now we've been able to extend that research and look at other materials and see how they're going to behave and how the plants are going to behave. So let's recap what we've discussed. In Soil Moisture 101, we've gone over the basics of water content and water potential. In this current webinar, we've gone over we've taken a deeper look at water potential. But and soil moisture release curve, but we've primarily just focused on the states of water. What are we missing? And a lot of it depends on what the end goal is, but one piece that we're missing is flux data and rate data. We briefly touched on hydraulic conductivity, but that's another important factor. And this is going to be a focus of our next virtual seminar, is being able to measure hydraulic conductivity and water movement in soils, and help ultimately to tie that to the big picture, which is understanding ecosystem fluxes. So we've touched on storage. Now we're going to jump over to rates and movement of water, and then eventually we'll move beyond that and hopefully tie everything together to help us understand ecosystem fluxes. And now we'll move on to questions.
Awesome, thanks, Leo. So it looks like we have maybe about 5 minutes or so to take some questions from the audience. And thanks to everyone who's already sent in questions. There's still some time to submit those if you'd like to. And we'll try to get it to as many as we can beforehand. If we don't get to any questions that you have asked, there will be people, Leo and others, who will be able to respond to you via email to your questions. So let's see. Here's first one here says, okay, so this one says, Leo, that I've heard that the measured field capacity can vary depending on whether the soil has previously been in a dry or wet state. Is that true? And if so, how big of an error margin might that cause if I plan irrigation scheduling according to field capacity?
So that's a really good question, and that is another factor that can limit field capacity. And what you're looking at is actually the effect of hysteresis, because depending on the soil type and how big the hysteresis can be, it is going to affect what it actually shifts that field capacity point. So depending on if we're on a wetting or drying curve and how we irrigate, it actually is going to change how the soil is going to hold on to the water. Now, if we know what a water potential point to irrigate to, then we can irrigate to water potential and not just water content, and still be able to control that, but we need to understand how that's going to shift at what water contents our field capacity point is going to be at. So it is important to understand that.
Okay. Let's see. This next one here. So we're currently monitoring soil moisture through gravimetric water content and volumetric water content. How can we integrate these into a soil moisture release curve?
So that's another really good question. It's a little tricky. Obviously, one of the better ways to do this would be if you could actually take some samples and actually measure the soil moisture release curve for that soil, because then you can actually take that and use your measured gravimetric or volumetric water content points to set your irrigation points. So if you know what those points correlate with in terms of water potential, then you can set your points from there. So that would be the best way to do it. And another option is actually modeling it out. So if you know some information about the soil, you can there are things like pedal transfer functions where you can input those variables and predict a soil moisture release curve. They're not as accurate, but it's another option.
Okay. Here's one regarding matrix potential readings. Do they include osmotic potential? Like when there's salinity, does it affect the reading?
That is a really good question. And it really depends on what type of instrument you're using or sensor you're using to measure the potential. So for example, tensiometers and the granular matrix sensors and the things like the Terrace 21 and the MPS 6, those only measure matrix potential because of the way they interface with the water in the soil. So they actually are blind to osmotic potential. Laboratory instruments like the WP4C measure both osmotic and matrix potential, but there aren't really any good field sensors that are going to give us both components. So you would need to know more information to actually get out that osmotic component as well.
Let's see. Here's one. It looks like we might have time for one or two more here. How can you measure capillary water potential?
So capillary water potential is actually is tied to matrix potential. So if you're measuring matrix potential, you're essentially measuring the effect of the capillaries or those different pore sizes. So that would be the best way to try and get at that, would be to actually measure matrix potential, because that's primarily what's governing matrix potential.
Okay. That looks like that's probably all the time we have right now. Again, if we didn't get to any of your questions, we have these recorded and we will be able to get back to you via email. And so look out for those emails coming in regard to answering your questions. And that's going to wrap it up for us today. Thanks again for joining us. We hope you enjoyed this discussion, and thanks again for all of your great questions. Also, please consider answering the short survey that will appear after this webinar is finished to tell us what type of webinars you'd like to see in the future. And look for the recording of today's webinar in your email. And stay tuned for future Meter webinars, and have a great day.